Welcome everybody. Let's continue our discussion of trigonometric substitutions. So when we encounter a potential trig substitution, this is really the question that we are always asking ourselves. We are really saying, which trig substitution should we actually use in a given situation? And for that, we're kind of coming back to our Pythagorean identities as our prototypes. Now, what those were, remember that if we had a 1 minus sine squared, that gave us a cosine squared. If we had something that looked like a 1 plus tangent squared, that gave us a secant squared. And if we had a secant squared minus 1, then that gave us a tangent squared. Okay. Now, each one of these are kind of what we have in mind every time that we see one of these substitutions. So what happens here in the very first one, we see 1 minus sine squared, what that is kind of going to correspond to is we have something that looks like a squared minus x squared is going to tell us that. When we see 1 plus tangent squared, now we're looking at substitutions which look like a squared plus x squared. And when we see things like secant squared minus 1, then under the radical, that's going to remind us of things that look like x squared minus a squared. And so in each one of those cases, kind of what our substitution is going to be, it will be each one of the trig functions that show up. So if we see a squared minus x squared, we're thinking of a substitution involving sine. If we see an a squared plus x squared, we're thinking a substitution involving tangent. And if we see something that looks like x squared minus a squared, now it's going to be a substitution involving secant. And so that's going to really be our guide in each one of these situations. So if we then go forward and say, how would we actually evaluate this integral? So how the substitution would then go, we're really thinking, all right, we're seeing something that looks like x squared minus 16. And so the substitution that we have in mind is secant squared minus 1 being tangent squared. And so that's really what we have in mind there. Now, what's got to happen is in order to get this to actually work so that we could factor out something and use this, we need an extra factor of 16 in there. And so 16 that's squared. And so what we can do, we can say, let's do a substitution with x equal to 4 secant of theta. Okay, so x squared being 4 secant of theta, our dx then becomes 4 times the derivative of secant, which is secant theta tangent theta d theta. And so what happens when we make this substitution, that we get 4 secant squared theta, oops, not squared yet, not there anyway. So 4 secant of theta squared minus 16, which looks like 16 secant squared theta minus 16, which in turn gives us 16 secant squared of theta minus 1, or secant squared minus 1 gives us tangent squared. And so what happens is this becomes our substitution. So we know what x is, we know what dx is, and we can essentially choose the correct u substitution. So let's do that. All right, so what we have for our integral of x square root of x squared minus 16 dx, we said x was going to be 4 secant of theta. dx was then 4 secant of theta tangent of theta d theta. And we said that our stuff under the square root, our 16 minus x squared, when we substituted everything, just became 16 tangent squared. And so if we substitute all of this in, what happens? Well, I have a 4 secant of theta. Then underneath the radical, I've got 16 tangent squared. And then for the dx, I have another 4 secant of theta tangent of theta d theta. So when I simplify this now, we can get rid of that square root. So now we've got an integral of 4 secant of theta times a 4 tangent of theta when we take the square root times a 4 secant of theta tangent of theta d theta, which gives us 4 times 4 times 4. So we get a 64 on the outside. So we've got our 64 as our 4 cubed. Then on the inside, we've got 2 secants. So we've got a secant squared. And then we've got 2 tangents for our tangent squared. And so now we are kind of back in the case of what we were doing before when we were doing our trigonometric integrals. What do we do whenever we have powers of the secant and tangent, and those powers are both even? So remember when we've got the situation where our secant squared was going to be even, then we could really just kind of have everything set up to do a u substitution with u equal to tangent theta, so that our du then just becomes secant squared of theta d theta. And so this thing becomes a 64 integral secant squared theta d theta becomes my du, and tangent squared becomes u squared. So that I end up with a 64. Integrating that, I get a 1/3 u cubed plus c, which ends up just being a 64 over 3. U was tangent, so a tangent cubed theta plus c. Okay. So this kind of gets us our integral. So now this evaluates our integral, but now we've got it evaluated in terms of theta. So what we need to do is go back to our variable x. That was what we started with. So let's do that.